Hello everyone, and thank you for attending this next video evidence training webinar. If you missed the last webinar last month, those are now available online on our YouTube page. We'll make sure that we give everyone an email once this webinar is completed so that you can have a link back to that. Last week we were covering fundamentals of the digital evidence workflow as files are being transported through various multimedia frameworks. And today's webinar for this month is going to focus on aspect ratio considerations for the video technician and video analyst. This topic is one that spurs a lot of debate in our community, which is a good thing, and I think really gets to the inherent point that this technology is not simple, clear-cut, and dry. So I'm going to begin this webinar by exposing the attendees to a bit of a history on why we are where we are today, talk about various limitations and issues that arise with aspect ratio, and then we also thankfully today have Larry Compton from Ocean Systems on the line as well. Larry will be jumping on to complete this webinar towards the last 10 or 15 minutes or so of the webinar. So again, for those of you who don't know me, my name is Andrew Fredericks. I am a certified forensic video analyst with iNPUT-ACE. We'll get to some various things within iNPUT-ACE later on in the webinar, but the point of this is to focus on the aspect ratio considerations. So aspect ratio, it's a word that is used a lot in our industry. It's a word that's misused a lot in our industry. And what aspect ratio refers to is the ratio between the width and the height in an image. The reason that causes so much confusion is because the ratio between what in the image. That's really where the various aspects of aspect ratio get a little bit complicated. Because aspect ratio can mean many different things. It can mean the pixel aspect ratio using the acronym PAR, P-A-R. It can also mean the picture aspect ratio using the acronym PAR, P-A-R yet again. So that already should have some head scratching because why are we using the same acronym to mean two different things? It can also mean the sample aspect ratio and the storage aspect ratio. And yet again, we're using the same acronym to mean two different things. It can also be the display aspect ratio. This little part alone should be a little confusing. And people in our world are confused on the forensic side, but so are the people who are making this CCTV technology itself. If you go read on any forums online or through any software development forums talking about the development of various video technology, these debates go through that world. They go through the world of people that are manufacturing the DVRs themselves, and we see that in the way that these DVRs are coded. Sometimes those acronyms are misunderstood and misused, and that really ultimately matters for us when trying to interpret and view digital video evidence. So I'm going to focus on the three areas of aspect ratio that I believe matter most, and those are the display aspect ratio, the pixel aspect ratio, and a new one that I'm going to introduce that I'm going to call pixel dimensions. And I want to use those words carefully here so that it's quite clear what we're talking about. We're going to go through each of these three in the rest of this presentation here. Starting with the display aspect ratio, which is the relationship between the width and the height of the intended image playback. So what I mean by that, if we look on a TV back here, that the width is going to be 4 for every 3 of the height. Now another way of saying that is that for every 4 inches across the width of the TV, we're going to have 3 inches up and down across the TV. And when an image is intended to be displayed at 4:3 on a 4:3 TV, if we were to display that same image at 16:9, everything would be quite stretched. And that's why display aspect ratio is quite important for us to understand. Standard definition is most commonly at that 4:3 ratio, and HD is most commonly at 16:9. There are exceptions. We're going to simplify things a bit during this webinar. So again, as I said earlier, the images have to be displayed at the correct shapes in order for, at the correct display aspect ratio in order for shapes to be correct. So a 4:3 image needs to be displayed at 4:3 in order for shapes to be correct. Pixel aspect ratio is a little bit different. Pixel aspect ratio refers to the relationship between the width and the height of an individual pixel in the image. So a pixel, again, is a picture element. If we zoom down into an image, like here in the tire of this vehicle, once we get down as far as we can possibly get down in a digital image, we're looking at individual pixels. They are indivisible. They are one solid static color value when displayed on a digital monitor. Now again, that can get a little confusing when we talk about things like color spaces and different channels of color. But let's simplify this and just say that when an image is displayed on a digital monitor, it has one single square color value. If we were to zoom into that, we're going to have one bigger square color value. This isn't CSI. We can't zoom in off of a mirror in the background, see a series of pixels, and zoom in and get someone's face. That's science fiction. That doesn't exist. A pixel is going to be indivisible in the real world. And they are square shape on a digital monitor. So if pixels are square in shape, as I just said, why isn't the pixel aspect ratio always simply 1-to-1? In other words, a square is going to have an even width to a height. So the width is always going to be the same length as the height in a square shape. So if I'm saying that pixels are square shapes on digital monitors, then why aren't the pixel aspect ratios always just simply 1-to-1? Well, if we were talking about digital signals from the start, it would be 1-to-1 in theory. At least it should be 1-to-1. But we don't always have digital signals right from the start of our workflows because analog technology is still frequently used at the level of the camera, sending an analog signal, which is then digitally converted to produce a digital image that we're displaying on our digital monitor. And in that world, things do get a little bit weird. So let's take a quick diversion to talk about analog video in general. What is analog video? Well, here's a bit of a simplification of what an analog signal can look like. It's a series of waves at modulating frequencies that are basically run across the TV. They're continuous time, continuous amplitude signals, meaning that there's no discrete moments or events that are any more or less important than the other discrete moments or events. It's just simply continuously changing and being written across the TV. It does not have a concept of pixels. So analog video, again, is this this continuous changing time and amplitude signal. Really quickly, I'm going to talk about the way that old CRT TVs would work. I'm going to focus this whole webinar, by the way, on NTSC video. So if you are in a PAL country, I apologize, but we don't have the time to go over the intricacies that are going to arise from that. So I'm going to primarily focus on NTSC. Now, in the CRT world, an electron beam is focused through a vacuum tube, and those electrons end up striking the front of a tube and lighting up the TV. Now, the line that is being written across the TV is going to be able to be changed in terms of its brightness all the way across the TV. So essentially, this signal, if this were a horizontal line across the TV, has a modulating changing brightness value as it gets written across the TV, and it's going to happen 525 times across the TV. Now, not all of those contain visual data. I'm going to simplify things here, and let's just say that 480 of those do involve visual data. Again, go read online if you want to see some additional complications with this. But after removing the non-visual components, like the blanking intervals and then doing some rounding, we get down to 480. And this is what the standards that were written to discuss how NTSC video should be on the digital world. They established a standard talking about those 480 lines containing that visual information. Again, this does get a lot more complicated, but I'm simplifying things here. So again, as I said, in referring to the number of discrete components up and down across an image, we're able to quite easily get to a number of 480. Because of the way that the old technology and the old hardware worked, we have 480 lines up and down across the image. But there's no real defined width. Because we're talking about discrete moments in time as being what would define a width, and because this is a continuously changing signal, there is no discrete individual entities across the width of the image. So those 480 lines, which is 280 or 240, which is half that in the field, go look up analog interlacing if you want to read more about this. But again, there's no defined width. This might be quite confusing at this point, but let's now look at what that looks like when we sample this in the digital world. So in the analog world, we have these discretely sampled points in time across the signal that are going to give us values across the width of the image. Our goal is to convert that signal into a digital one by sampling it at those moments in time and converting what was a continuously changing frequency into discrete samples that become our digital signal. So if you remember from the previous slide, we've got that 480 height and an undefined width. Now the real question for asking how many times we're going to sample this across the width really boils down to a question of, in how short of a region can the light really change in the analog signal? Now another way of asking that question is, how far apart are two discrete brightness values in this analog signal? Now if we look at what this example here is showing, we have a sample at this point in time that gives us a value, and a sample at this point in time that gives us a value. But that means that none of this data in between is being sampled. So if we were to sample at this rate, we would result in a digital signal that is essentially quantizing the values and only giving us individual values at certain points in time. In other words, we've reduced the quality a little bit by doing this. So what if we increased the number of samples that we had? And what if we added a sample here, here, and here? So now we're adding a sample in between these additional samples. It would give us more values on our digital world, and we would have higher frequency, we'd have a higher range of values, we'd have pixels horizontally across the image, and a higher resolution, which could be a good thing. But why stop there? Let's add another sample. Let's now sample here, here, and here. Now we're adding two samples in between each of these. Now again, we're going to have more samples in the digital world, we're going to have more pixels across the image, and we're going to have higher resolution. But one of the problems here is that we could continually do this into infinity. If we were to always add an additional sample, we could have 100 samples between these two pixels here. We could have 1,000 samples. We could have 1,000,000 samples. We could have literally an infinite number of samples between each of these pixels in the theoretical world. But in the physical world now, we need to actually establish a standard that will give us a definitive finite number of samples across the image that will define the pixels horizontally in our image. That ended up coming about through a series of different standardization bodies that established a 13.5 megahertz sampling rate. I'm going to gloss over the math of this because it gets quite confusing and there's a lot of debates online. But basically after some math and various arguments between the different standards bodies, they settled on a 720 sample width when only 704 of that actually contain visual data. One of the big reasons for this is to allow for easy conversion between NTSC and PAL. But even then, the math gets really, really bizarre. So now that we have this 704 value that we've defined for the number of samples we're going to use for our width of our image, we have our 704 by 480 is a very easy sample to derive, which is also referred to as 4CIF. And I'll talk about that a little bit more in detail in a second here. But the basic summary, if you don't understand any of what I was talking about on the previous slide, is simply that various standardization bodies were combined to establish some common digital frame dimensions. Just walk away with that basic understanding that there are common frame dimensions, and the most common of which are going to be 704 by 480, 704 by 240, 352 by 240, and 720 by 480. All of these numbers we've seen on the previous slide, where the 352 by 240 is simply half of what we derived on that 704 by 240, or excuse me, 704 by 480 standard. There's a lot more. Larry's going to address some additional ones and probably double back and talk about this in a little bit more detail later on in this webinar. But the point here really is that there are standards that we're going to continually see in the digital CCTV world. And where things are going to get a little bit strange here is that most of these are intended to be displayed at a 4:3 ratio in most cases. So you might be asking yourself, if you're not familiar with this debate already, that doesn't make sense. That math doesn't work. 700 by 480 does not equate to 4:3. Now let's take a quick look at a calculator to prove that here. If I look at what 4 divided by 3 is equal to, that's a 1.33 to 1 ratio. But what is 704 divided by 480? Well, that is not a 1.333 ratio. That is a 1.466 ratio. Why is there a difference? It would be intuitive to assume that the ratios that we would have of our pixels would equate to 4:3 if they're intended to be displayed at 4:3, but they don't. And the reason for that comes back to our analog world being turned into a digital world. I'm going to try to simplify that problem with a bit of a visual here. So to repeat what we had talked about on a previous slide, the analog signal, if this were an analog image, this circle over here, it contains no defined width. It does have a defined height of about 480 pixels up and down. And we're going to sample this width based on that. Let's use the 704 pixel example that was established by the various standards bodies. And now if we sample this image at a rate of 704 pixels across by 480 pixels up and down, what that looks like is kind of like this. We have samples going horizontally across our image at 704 across the image and 480 up and down, which equate to non-square regions of pixels. So I'm going to look at this region, and this is an exaggeration of what is happening. But imagine if this were an 8x8 block of pixels right here. Well, in the analog world, once it's sampled, that 8x8 block of pixels is not going to be in a square shape. So once sampled, once we have these quote-unquote pixels, they're not intended to be square once they're sampled in the analog world. And the reason for that is when these standards were written, they didn't exactly have the concept of digitally displaying these as pixels on a digital monitor. We were still using analog TVs to take this digital signal and display back on the analog monitor. And so we were able to display those circular shape or square shapes on the analog monitor without issue. The problem comes in when we now have technology containing digital square pixels, and we take these discrete regions and we now display them as squares. Well, what ends up happening is we're taking the original raw data, we're displaying that exact same raw data, but now the image is going to be stretched because each of those discrete regions is forced into a square shape on the digital monitor when it wasn't intended to be a square shape in the analog world. So this now is our issue. And again, this is a big exaggeration. These images don't get stretched in this gross detail here, but I'm trying to highlight what's happening, which is that the analog signal is now being stretched in the digital world. So this is a bit of a problem for us, because if we're trying to talk about the shapes of objects, we're looking at shapes in a way that they weren't intended to be displayed in the first place. And we might want to correct them and get them to display back as they were intended, which is as circles or as squares. So very generally, our goal is to resize the image and take an image that looks like this and convert it to something that looks like this. But we have a bit of a problem because the digital world is forced into a square shape. All of our monitors have square-shaped pixels, so we can't simply change the size of those pixels. There's a hardware limitation with our digital world. Now, the absolute best case scenario on the theoretical world would be if we were to have digital monitors that had non-square shapes, but those don't exist. So we're confined by that hardware limitation. So since we can't change the size of a pixel, what we have to do instead is change the number of pixels. And the way that we change those numbers of pixels is answered by a term called interpolation. Well, what is interpolation? So interpolation is a method of changing the numbers of pixels and then, is coloring in these new pixel values after a number of pixels have been changed. Let me rephrase that another way. When doing a resize of an image, for example, if this image here is 3 pixels horizontally by 2 pixels up and down, and I want to change that to an image that is 3 pixels horizontally by 3 pixels up and down, what I'm really asking is, what color value should I assign to these new pixels? I had 3 by 2, I want to create 3 by 3. What color value should I create for these 9 different pixel values? Well, in this simplified example, it would make logical sense, I think, to color the top row in red and the bottom row in blue. But what color value should we assign to this middle row? Well, that answer is going to be answered, that question is going to be answered differently by different interpolation methods that we might choose. So 3 of the most common interpolation methods that we see are nearest neighbor, bilinear, and bicubic. There are many more. These are the 3 that I'm going to focus on in this particular webinar. And I'm going to now go into Photoshop and look at this exact example in Photoshop. and look at how Photoshop handles this answer, which is going to be the same way that any other program using these three algorithms will handle the same question. So here's a reproduction of our example in the PowerPoint, where we have 3 individual pixels horizontally by 2 pixels up and down in a red row and a blue row. To resize in Photoshop, it's quite easy. We're simply going to go up to our image drop-down and choose image size. And I'm going to change my width in terms of pixels from 3 by 2, now going to 3 by 3. And you can see here that we have our resampling options by cubic, nearest neighbor, and by linear. We're going to go through each of those in sequence, but let's take a look really quick at what nearest neighbor does first. So again, we have 3 by 2, and now we have 3 by 3. And nearest neighbor has simply added in a blue row of pixels across that horizontal line. So if we look back here in our question, what nearest neighbor has answered is, I have red on the top, I have blue on the bottom. I'm going to choose to add all of my additional pixels here based on the color value of my nearest neighbor. So this color value here finds its nearest neighbor, which happens to be the pixel below it. It chooses below instead of above because of the way that the algorithm is written. But essentially it's saying I'm going to copy the color value of the pixel that's closest to me, and I'm going to create myself as blue. This pixel answers this question the same way, as does this one, and our image looks like this. Well, that might be a bit of an issue for us if we were resizing in this way, and I know that this is a very simplified example, and normally we would be dealing with images that are something more like 704 pixels across by 480 pixels up and down, so things get a little bit harder to visualize, but this, I think, really highlights well that when using nearest neighbor, if we're going in increments that are not 100%, we end up getting stretched shapes and duplications in areas that we don't want. Let's take a look, though, real quick at what nearest neighbor does if we were to go in an increment of 100%. So what I mean by that is we're going to double all the pixels and resize this so that instead of having 3 by 2, we're going to go to 6 by 4. That's what I mean by an increment of 100%. It's a resizing of 200%. So instead of having 3 by 3, we're going to go to 6 by 4. Well, now we have what is essentially the exact same image. We just now have 2 rows of red and 2 rows of blue. So all of our questioned pixels in the middle here duplicated the value of the row above it and below it, and same as the horizontal side. And so what was an image that looked like this, now looks like double the size. So we've preserved all of our edges, we've maintained all of our pixels, we've just simply doubled them. So this would be a very good way for us to forensically resize an image while maintaining all the edge pattern. And the point of this exercise here is to show that when resizing with nearest neighbor, it's very important that we are only doing this in certain scenarios when we are resizing in increments of 100% or more. And I would never, ever use nearest neighbor when in resizing an increment that is not 100%. Now let's take a look at what happens if we were to resize this same image to our 3 by 3. But instead of using nearest neighbor, let's do something like bilinear. Well, bilinear is going to answer that question by interpolating the values and essentially averaging the pixels that are around the area in question. So now we have our top row of red, our bottom row of blue, and the color values in between become the average or the middle value, the middlemost value between those 2 points. So now we have an image that is a smoother transition between our red to our blue, and we can do things that are not in increments of 100%. Bicubic in this particular simplified example is actually going to answer the question in the exact same way as bilinear does. It's going to do the same thing because this is so simplified, but I'll show you another example in a moment where those two do begin to change. Let's take a look now at what bilinear does when we go to our 6 by 4 ratio. Now when we're doubling the size in both directions, we get an additional row of pixels. So again, we have this gradual transition from red to blue. And bicubic is going to do something, again, very similar in this simplified example. When we go to a 6 by 4 ratio with bicubic, it will do what is basically the exact same thing. So back now inside of our PowerPoint, let's take a look at another example where we're using an image that has a little bit more detail, or a few more pixels. So we now have a 4 by 4 pixel block where the outer ring is perfect black and the inner ring is a gray value. When we resize this up by ×4, so I'm going to take every single pixel and we're going to turn that into a 4x4 block of pixels. So this pixel right here is essentially turning into a 4x4 block, creating a much larger image. If we choose nearest neighbor, because I'm going up by 400%, again, this is an increment of 100%, so we're essentially going to maintain all of the edge pattern. We're going to increase the number of pixels that we have, but we've essentially created the exact same image, just a larger one, where we're representing more pixels with the same color value. So this is a very good representation of this image, and will be a great way for us to maintain our edge pattern. And by edge pattern, what I'm referring to is this hard edge where the color shifts from black to a different lighter color value. We've maintained that edge pattern just as it was in the original footage. All of our measurements would stay the same relative to one another, and we've preserved all of our edges. Now, what bicubic does is a little bit more complicated. What bicubic does is average out the questioned pixel values by drawing a smooth curve between them. So these black color values on the outer edge, we're going to essentially draw a curved line to the values in the middlemost area here, and that curved line is going to change the color values, ramping them up to a lighter color value and then back down again to our black. And that curved line, ends up going above the original color value that we had in this image. So essentially, imagine that in our nearest neighbor example, this is like taking your car and driving it around a corner with a very, very sharp turn. We're going to go at 30 miles an hour and cut left, and it's a very sharp angled turn where that edge is really prominent. It's a hard edge. In bicubic, we're going to slowly round the corner, and we're going to make it a very easy turn where we round and then kind of double back around the corner. It's like drawing a very smooth curved line. Bilinear is also going to produce a curved line, but it's less curved than bicubic. So where bicubic is going to go around and then back down again, what bilinear does is simply curve around the corner. So now we have this dark pixel over here gradually shifting to our lighter pixel values, then gradually shifting back out again to our black. But there's a direct linear change between the black to the value that we had in our original footage, and then back to our black again. So the differences between bicubic and bilinear are that bicubic has a much more gradual change that exceeds the values and goes back down again like a curve, and bilinear is simply a linear translation between the color values in the questioned pixels. That might be a little bit confusing, but what we're going to do now is look at a comparison of those three different results on a real case. So this is a homicide case that our office finished earlier this year. And what we're going to do is zoom into the area of the video in this region here and change the dimensions of that resized area using the three different interpolation methods and compare them. So here's our .nvr file. I'm going to drag that here into my iNPUT-ACE file list and take a quick look at the video. I'm going to zoom now into the video here in the area of interest. And we're going to observe this car pulling up. Some individuals exit the vehicle, and then ultimately they walk back to the vehicle with what is purported to be a body that they're carrying into the vehicle. And so our goal right now is to zoom into this area, to crop this, to resize this, and observe the object that they're carrying in their hands right now. So I'm going to go back in time here real quick, just frame by frame backwards to get to an area so I can make a quick clip of this footage, where I start my clip at an in by marking my I key. I'm going to now scan forward to about here just to make a very short clip, mark an O with my O key, mark an S to create a subclip. I'm just going to name this my clip. And now on our workflow tab over here within iNPUT-ACE, we're going to send that clip through three different workflows to compare the differences between them. So what that's going to look like is first a filter to crop my image. I'm going to take that subclip and crop the footage. Within the settings of this, I'm going to simply crop that one little area right here. Now that I've cropped my region of interest, I'm going to apply another filter to resize that cropped area. And inside of the resize settings here, let's take this dimensions and let's multiply it by ×4. So this has now scaled my footage by 4 times, and I can now choose which interpolation method I'd like to use between my bilinear, bicubic, and nearest neighbor. Let's use my bicubic first, and then next I'm going to add a levels adjustment node to really exaggerate the edges of these pixel blocks. So what a levels adjustment node does is allow me to trim my color values, exaggerate the edges in the object, and clip out any values on the outsides of this area. Now that I have a levels adjusted image, I'm going to do this exact same workflow 3 more times. So I'm going to duplicate my crop node, my resize node, and my levels adjustment node, and I'm going to do that 1 more time. All of the values inside of the settings for these are going to stay the same, but now what I can do is simply connect up an additional workflow directly through these same nodes, but I'm going to change the value of my resize node so that the resize is done in different ways for each of these 3 different workflows. So now this resize node, if we recall, was using bicubic. This resize node I'm going to change to using bilinear, and this resize node I'm going to change to using nearest neighbor. Everything else is all the same. Finally here, I'm going to go into a canvas editor node, and I'm going to take my levels adjustment outputs into a canvas editor to make them play back side by side. And now I can take the results of that canvas editor, and I'm going to place those into an MP4 file in my output directory here. We'll just call this comparison. And let's speed that up a little bit. And let's process that workflow. So here's my results of my comparison. I'm going to now interrogate those, and let's zoom in and take a look at the differences. So again here, what we had was our bicubic results on our left-hand side, our bilinear results on our right-hand side, and our nearest neighbor results underneath. And we should be able to see pretty dramatic differences between them. Now the differences between bicubic and bilinear aren't as severe, but look at the line across this white transition between the white and the black right here. Notice that this line is a rather smooth line, and the line here is a very jaggedy line. That's because bicubic will smooth out the footage much more than the bilinear will, and bilinear is going to leave these harder edge patterns. Now we can still see the object that those 2 individuals are carrying in better detail in both of these images. Now let's take a look at what nearest neighbor does. Well, nearest neighbor has preserved all of those pixel values, all of those hard edges, and in my opinion, as an observer of this, although this is more similar to what the DVR actually recorded, I, as a jury, for example, would find this much harder to look at. So although this is a better representation of what the DVR actually recorded, if I was to present this to a jury, it might be important to show them something like this to report what the DVR is actually recording. But in a demonstrative exhibit where we're talking about the actions that the individuals took, it's much more pleasing to the eyes to observe these 2 sets of data. So essentially, the argument here is, for forensic purposes, when we're trying to measure objects or we're trying to state what was recorded by the DVR, it's important for us to look at what the DVR actually recorded and do things like nearest neighbor interpolation when resizing in increments of 100%. But when presenting something to a jury as a demonstrative exhibit to talk about what activity occurred, it's much easier for them to look at something that's been interpolated with bilinear or bicubic. And I would argue that because bicubic is smoother than bilinear and easier to look at, it's an easier and better thing to present for demonstrative purposes. Again, we're already not looking at the raw original pixels, so I might as well create the prettiest picture if that's my goal. Now the statement of "if that's my goal" is rather important here, because the question of what kind of interpolation to use really boils down to a question of what is my goal? What am I trying to accomplish by resizing? Am I trying to accomplish a pretty picture to display to the jury, or am I trying to accomplish a forensic need that might require using something that is going to preserve those hard edge patterns? So here are some basic rules of thumb that I tend to use when doing resizing. Nearest neighbor is great for maintaining edge pattern. It's great for not introducing new color values because it can't introduce new pixel values based on the way the algorithm works. Again, it finds the nearest neighbor and it copies that value. But you should never use nearest neighbor unless you are resizing in increments of 100%. If you were to use nearest neighbor and resize in increments of not 100%, like let's say we were to go from 704 by 480 to 640 by 480 or anything else, we're going to be removing pixel values just at arbitrary intervals, which will change the relationships of objects from one another, and that would be a very bad thing. So do not ever use nearest neighbor unless you're resizing in increments of 100%. In other words, 100, 200, 300%, etc. It's arguably the best for creating forensic measurements and to report what was actually recorded by the DVR. Bicubic is great for creating pretty pictures. It's going to create the smoothest images out of those three options, and which makes it the best for creating demonstrative exhibits. Bilinear, on the other hand, is a very happy medium between the other two options. It's going to create smooth images, but not quite as smooth as bicubic, and it's arguably the best option for doing aspect ratio corrections. So really, the three primary reasons that I would use these different interpolation methods, if my goal is for forensic purposes to resize and show what the DVR recorded, I'm going to use nearest neighbor in increments of 100%. If my goal is to create a demonstrative exhibit with a pretty picture, I'm going to use bicubic. And if my goal is to create aspect ratio corrections where I don't want to smooth out the image too much, I'm going to use bilinear for those corrections. So now we're doubling back again here to the point of this webinar, which was aspect ratio corrections in general. Let's look at a quick case example where we are looking at an individual entering a building in a normal style of video that we'd receive. This is another homicide case. I'm going to clear out my file list by simply using my delete key to clear out the file list. And I'm going to clear out this complex workflow here and remove that simply again with my delete key. So now back in my folder over here, I'm going to grab an example using this footage. This is a DAV file that we could play inside of a proprietary player by simply dragging that DVR file into the player, and it would display the image like this. So is this image being displayed correctly is a very important question for us. You know, are shapes accurate? Are the original pixels being displayed on screen right now? And if we look at the dimensions of this image, it's reporting that the dimensions of the image are 450 by 342. That is nothing like any of the other standardized file sizes that we were looking at previously. And 450 by 342 is a very strange size. Excuse me, 450 by 342? Yes, 450 divided by 342 is equal to 2.16, which is a very strange size. 450 divided by 342. Yes, excuse me, I must have misclicked there. That's 1.31 to 1, which is still a very strange size. It's not the 1.33 to 1 that a 4 by ratio would be, nor is it the dimensions that we would expect from the original recording. And even worse, if I grab this image and stretch it, I can make this look like anything that I want it to look like. So when we get to an area of an individual like walking into the scene, like this individual right here, for example, what was the shape of the logo on his shirt? Was it something very stretched and skinny or very wide and thick? There's no way for us to really know using the proprietary player alone. What we're going to do now is take that same file and drag that into INPUT-ACE and take a look at how this is reported inside of INPUT-ACE's Interrogate tab. When I interrogate the image and play it back, you'll notice that the pixel dimensions reported down here into our metadata location are very careful in describing that we're looking at the pixel dimensions. We're not looking at aspect ratio, because aspect ratio, again, as we looked at before, has so many different things that aspect ratio can mean that we're very cautious here in describing that the pixel dimensions, the actual pixels that are in the file, are 704 by 480. Now, as we've looked at throughout the other examples, that's likely not the correct display on a digital monitor, because the digital monitor contains square pixels and are likely stretching the shapes of the objects. So that's quite important for us when we're doing things like comparison reports. So if I were to compare this recorded individual on this video to the clothing that might have been seized after a homicide, I should be very cautious in ensuring that either the shapes are being displayed at their correct shape, or that at least we understand that they aren't. So what I mean by that is, if I was to observe the shape of this shoe, for example, right now it's being displayed at 704 by 480, which is slightly an incorrect shape. It's slightly too wide. So I might want to correct that. So let's look at how easy it is to correct these. And now we're going to take everything that we've talked about previously and boil it down to the simple, practical things that we should be doing when relevant in a case. What I'm going to do here is mark a series of images that we're going to use for example, a comparison report. And let's change the width to the height ratio by using a very simple resize. So I'm going to mark this image with my M key. I'm going to call this maybe his shoes. It's a good image of his shoes. I'll move forward here to how about an image of the side of his face. I'll mark this and call this left face. And maybe I'll grab another image of his left shoulder area here. We'll call this top of left shoulder. So now I've got 3 marked images very quickly by simply using my M key. We can even see what looks like is potentially a marking on his neck here. So I might use my M key here and we'll call this neck. Now we have 4 quick, easy marked images. I'm going to toggle over to my workflow tab. I'm going to create a new filter using a resize node that is simply going to resize each of those marked images. When we open up the settings of my resize node, again, we see that the width is 704 by 480. We're going to change that to something that is 4 by 3. So what is a 4 by 3 ratio using the 704 by 480? Well, again, 704 divided by 480 is 1.466, and 4 divided by 3 is 1.33. So how about I just simply multiply my height by 1.33? So what is 1.33 times 480? That is 640. So that is an easy width that I can use where I can change the number of pixels from 704 to 640, and now we have a 4 by 3 ratio where the shapes are going to be much more accurate to how they would have been on an analog signal. Now we can choose our interpolation method, and going back to what I was arguing previously, when doing ratio corrections, I would generally use bilinear. So I'm going to correct this using bilinear, and now we can save that out as a bitmap image. Again, let's go out here to my output directory. I'm going to save the files based on the same name of the original file, connect that to my output to bitmap, press execute, and already I'm done. And in my output folder, we now have each of those images corrected to my 640 by 480 ratio. Once we have a workflow like this created, we can very easily save that workflow by simply going out to my workflow actions here and pressing save. And I've now overwritten a previously named workflow called 4 by 3 aspect ratio correction. I could also save this as a new workflow. I can name this something like aspect ratio bilinear. And now anytime that I want to come into the program at a later point in time, all I need to do is reload that workflow, and it's going to reload everything in between. And I can simply connect my files up to that workflow, press execute, and have the correction be done for me. Now, things again have been a little bit simplified here. We likely would want to validate that it is actually intended to be a 4 by 3 ratio. Not all of the DVRs are intended to be 4 by 3. There are a lot of additional complications in here. A couple of the additional strategies that people use in these cases are to find objects that we can measure, like, for example, things that are intended to be exactly square or circular. Like if we were to zoom into a tire in the background and look at the circular area of the tire, we can measure the width and height of that tire to ensure that it is being displayed at an even ratio, and that those are indeed a circular object, and that we've resized our image correctly. This is, again, we're trying to do all this in 1 hour, and there's only so much we can accomplish in 1 hour. So there's 2 critical questions that I'm going to end on here before turning this over to Larry Compton. And the questions are, is the image displayed at its highest resolution, where resolution is defined as the ability to identify an object or edge in an image? So how is my ability to identify an object or image impacted by potentially doing resizing? And the argument here, I don't know if I'm going to have time to go through another example highlighting this, but the highest resolution in an image is going to be its originally sampled pixels. We're never going to get a higher resolution by doing any resizing, because again, looking at the interpolation methods that we're applying, we're going to either be applying smoothing in the case of bilinear and bicubic, and that smoothing is going to impact our ability of identifying exactly where that object starts and where that object ends. because the object is being smoothed out and rounded. Again, highest resolution here is not counting additional things like levels adjustment filters and frame averaging that we can apply. I'm purely talking about resizing at this point. So the question is our image displayed at the highest resolution? And one of the limitations here is that our highest resolution is always going to be our originally sampled pixels, but that's going to conflict with another question, which is, are the objects displayed at their correct shape? And that question is only going to be answered correctly when we've done resizing in the case of analog signals. So again, because analog signals have non-square pixel areas, we might need to resize the image in order to create accurate shapes. And now we've got a bit of a conflict because we're only going to have our highest resolution in the case of displaying our originally sampled images. But if we change those originally sampled images and we resize them, now we are going to get correct shapes, but we're going to lower the resolution. So do we want highest resolution? Then we shouldn't be doing any resizing. Do we want correct shapes? Then we need to do the resizing, but we're reducing resolution. And we have to decide which is best for our particular question at hand. For example, if the case involves looking into a vehicle to identify motion and activity of an individual, we're going to want to ensure we have the highest resolution, and we might not care that much about shapes. So in that case, I would argue that we shouldn't do the resizing, and we should leave it at its highest resolution, and maybe in our footnotes in our report, acknowledge the fact that they might not be the correct shape, but that's not necessarily a relevant question at this point in time. So really the question is, should we correct or should we not correct? Is it better to have highest resolution images, or is it better for us to have the correct shapes? That's really the question at hand that gets answered differently depending on the different scenario at hand. And at that point, I think I'm going to come to a conclusion here and begin to turn this over to Larry. So bear with me 1 second while I pass controls over to Larry Compton. Larry?
Yes, sir. All right. Well, Andrew, thank you very much. First off, thank you for having me on the webinar. This is a topic that I think is near and dear to my heart. I put some significant research into this and really like to see community discussion around it and would like to see a lot more. So I really appreciate the opportunity. With that said, I don't really have a lot to add. Andrew and I agree on much of what his presentation and discussion has entailed. We have some minor differences, and I think the biggest one being whether or not to resize. And with that said, it's interesting because I think we both agree, you know, a little bit further down the line. So what's important for me to say and get across in this webinar are for us as the technicians and analysts who have the training and experience, we are the knowledgeable ones, more knowledgeable than the average person on aspect ratio, and even, quite honestly, more knowledgeable than many video producers who've been working in the field for decades. Because of they don't need that depth of understanding. We do when we're determining what can and cannot be said by a video recording or an image from a video recording. So it boils down to what questions are being asked of the image and video. Who is going to be viewing it and for what purpose? And how will they be viewing this image or video? So those are the three things that I'll always put up front, and based on my training and experience, apply logic to produce my workflow and my outcome. Andrew mentioned earlier, and this is just kind of a side note, the luminance sampling rates and how important that is to our standards in regards to capturing uncompressed NTSC via ITU 601, and that sampling rate was 13.5 megahertz. Later on, as digital technology continued to evolve, and DV standards were created, for instance, sampling, it was determined and agreed upon that the square sampling rate would be 12.273 megahertz per second. So as Andrew indicated, with the analog signal, we have no defined edges, and the center of the image is critically important. With the new sampling rate of 12.273, luminance sampling rate, I should say, that is key because most digital CCTV recording systems that are sampling an analog signal, black box digital CCTV systems, they are sampling using a luminance sampling rate of 12.273, which means they're sampling for the purpose of storing square pixels. However, in the early days of the transition from analog to digital, many of the DVRs stored to formats designed and intended to hold non-square samples. So that, for instance, the 704 by 480, or 720 by 480, or 352 by 240, etc. Those are formats that were put in place by various organizations and standards bodies for the purpose of storing those non-square samples and then going through a digital workflow and being put back out to an analog medium or an analog-based display, CRT-based display. As the technology continued to progress, of course, well, now we have all digital monitors predominantly, still analog monitors out there, but the vast majority are digital. So we're actually taking the information that was sampled using a luminance sampling rate to capture square samples, storing it to a non-square raster size on the digital CCTV system's disk, and then we want to display it on our computers. We're no longer putting it out to, in most cases, an analog monitor or analog videotape, for instance. So it really becomes important to understand, I think, that piece of it, as well as the standards themselves, and this comes through training and education. On my screen, I have a chart that I put together last year with Ocean Systems peer-reviewed, sent this out to a number of people as I was doing development and research on this. And the chart is basically some video and computer display standards, particularly video standards as they relate to digital CCTV evidence or analog CCTV evidence, and how those are intended to be displayed at a 4.3 DAR. With that said, most analog CCTV cameras, meaning a CCTV camera that is transmitting an analog signal to the recording device or storage device. I have yet to come across an analog based camera that is intended to be displayed at any other aspect ratio than 4:3, with the exception of the 960H standard, the newer 960H standard, which technically requires a 960H capable camera and sensor, as well as a 960H recorder, but I digress. So with that said, this chart gives you what the standards are in, as far as pixels dimensions in regards to the non-square sample lines, samples and lines, and then how they should be displayed in a square pixel environment in a 4.3 DAR. And we go through NTSC, PAL, DV, DVD video, which has many standards. Lots of people not aware of those types of issues. CIF, and what is CIF? There is one resolution for CIF, 352 by 288. However, there is also SIF CIF, which is source input format, not common intermediate format. I say one size for the technical CIF. There's, of course, what Andrew had mentioned, 2 CIF, 4 CIF, 16 CIF, so on and so forth. So for all of these, we've done the math for you and provided you with this handy-dandy chart, and then on the next page we talk about our methodology. I think this is important because of those two luminance sampling rates that I mentioned. The issue really is there are only two when it comes to a 4.3 source signal being sampled. These are the only two pixel aspect ratios for displaying that 4.3 source. Now there are other factors that we see all kinds of aspect ratios from these analog sources. Some of them are the developers choosing to just read the way it's stored to disk. Some of them they round to make it more computationally efficient, so on and so forth. But if it's a 4.3 analog source, NTSC source, designed to be displayed 4.3, this is the actual sample, the pixel aspect ratio. Same with PAL. And then we get down into talking about that methodology, mentioning 960H and how it requires both the camera, etc. And then we show some computer graphics display standards, common computer graphics display standards. Again, where we have these things merging. We now have, for instance, UHD and 4K, which are both display standards and video standards. And so things are starting to standardize and come around to normal. So I really just wanted to show that chart and talk a little bit about investigative processing and forensic processing and whether or not to correct, as Andrew, when he tossed it over to me. In my workflow, I'm always asking those questions. You know, what questions are being asked of the video, who will be viewing it, and how's it going to be viewed? I'm the one with above average knowledge compared to the average citizen. I've been trained through, you know, various sources and so on and so forth. So I want to control it as much as possible. If it's going out, for instance, it comes down to an investigative processing versus forensic processing. And with investigative processing, for instance, putting out bolos or video clips for distribution, I want to control that. I want to ensure that I don't leave it up to the software to display this at the proper aspect ratio, because as we probably all know, regardless of who makes the software, there are format limitations, codec limitations, so on and so forth, that all play a role in this confusion and how things get displayed inaccurately when things are done behind the scene. So I want to control that. So if it's for investigative processing, a bolo, or to distribute the video, I correct aspect ratio before producing those types of derivatives. However, for forensic processing, I agree with Andrew, and I will not correct aspect ratio typically for interpreting things at the very, pixel level. And so I'm always submitting my originals anyways. I have a detailed understanding and explanation of why I'm doing what I'm doing and when I'm doing it, creating derivatives. I like to control and ensure that the bolos are at the proper aspect ratio so people don't appear shorter and fatter or taller and skinnier than they should. Same with objects depicted in the video. And the one question I often get with that in regards to NTSC, the last thing I'll end on here is, why do you downsize NTSC rather than upscaling your images? So for instance, rather than 720 by 480, why do you downscale to 640 by 480? And really, the sample size, the shape of the actual samples is not affected or determined by the number of horizontal scan lines in that original analog source. It's actually determined by that luminance sampling frequency. So I always maintain the number of horizontal scan lines and just correct the shape of the samples. Downscaling with NTSC often, does have a minor improvement in the correction in that it may improve your signal to noise ratio. So those are the things that I just wanted to touch on. If you're interested in this chart, it's freely available on Ocean Systems website as well as the DME Resources website for download. Just search for aspect ratio chart, and I hope that the discussions on this topic continue throughout the industry and we can get some standards put in place. Thank you very much for having me, Andrew.
Yeah, thank you very much for joining, Larry. We really appreciate having you on here. I'm going to now open this up to any questions that anyone may have. So please feel free to enter questions in the GoToWebinar panel. Give me one quick second here. I'm going to take over the presentation controls as well. So one thing, kind of doubling back on Larry's question here, I see a couple of different questions have come in about the resizing horizontally versus vertically issue. And for those of you who aren't as familiar with what that question is asking, what we're getting at here again is that the analog signal was supposed to be 4:3, but we've currently got something like 704 divided by 480 pixels. So to correct this, to make this 4:3, mathematically, we could change the 704 to 640 and leave the 480 the same, which gets us to 4:3. Or mathematically, we could change the height to 704 divided by, 528, I think. Yeah, there we go, 528. So we can resize the height up to 528. So the question in the industry is it better to resize down across the width or up across the height? There are a lot of differences in opinions on this on this debate. I recommend that you do your own testing to see the differences and what kinds of things that affect. The one thing that I'll probably add to Larry's statement, which I think he actually did touch on this, but I guess I'll just drive the point home again, is that if we were looking at very small changes at the pixel level between color values, like let's use the example of a completely black image with a single red color value. In fact, I actually have an example of this that I've mocked up. Let me go really quickly here into a sample that I have that'll highlight this issue, I think, pretty well. Okay, so I have an image here that, again, is not a real-world image. You're never going to see this in the forensic world, but it'll hopefully highlight what's happening at the pixel level when we do these various resizes. Let me bring in my navigator so we can really zoom into this. So what we have here is an image that is 704 by 480 across with these blue areas interspersed in the red image. And at the very center of the image, we have a series of blue pixels. They're kind of scattered at random intervals. So if I remove my, my extras lines, we can see what that looks like here. If I were to resize this now down to 640 by 480, for example, using something like bilinear, the result of these various pixels is going to get a little bit strange. Once I've resized this, you'll notice that some of the pixels that are along the middle stay as one single pixel. Other pixels now have this kind of faded look to the left as they're being interpolated, and other pixels on this side have the fade going the other direction. So if we are trying to identify what is the edge of this object, well, the edge of this object hasn't changed, but the edge of this object kind of has. So where would we identify the edge of this object? Now again, this is not a real-world example, but I think it hopefully highlights the concern that I have with doing the resizing and then ensuring that we're still maintaining all of the edges between our various objects. Arguably, if the shapes don't matter, I wouldn't even do the resizing in the first place for this exact reason. If we were to instead have done this resizing vertically, where we have now gone from 704 up to 528, we're still going to encounter a very similar issue where the shapes of the objects are being shifted. But you will notice, though, that here in some of these we now have 3 subtle color changes, where in the other one we only had the 2. So the reason I'm showing this is that the interpolation is going to affect the image either way, whether we go vertically or whether we go horizontally. But if we're looking at very small areas, I probably would recommend doing the vertical shift, just that we don't inadvertently remove color values that might be relevant to us. I have another question about where we can get a copy of those documents that Larry was showing. Larry, do you want to, you did answer that question already, but do you want to jump back on and address that?
Sure. Yeah, I just got an email regarding it as well. So on the, if you go to the Ocean Systems website, oceansystems.com, click on the Store button, that'll take you to our online store site, which also includes some forums, blog, and various other resources. In Google aspect ratio chart, it's there, as well as on dmeresources.com, my personal website. If you go to that site and just do a search for aspect ratio chart, I've made it available there to the public. You don't need to be a member of the site to get access to it.
Great, thanks, Larry. So I see another question about how do you know if the image is supposed to be displayed at 4:3 or at 16:9? And I think the easier answer to that question is that most often when we're seeing those various standards like the 704 by 480, 704 by 240, most often those are intended to be displayed at 4:3 from the analog signal that's been converted now to a digital signal. 16:9, we're pretty much, and maybe Larry, you can correct me if I'm wrong here, but 16:9, I think we're only likely to see square shapes to begin with anyway in the digital world. Would you agree with that, Larry?
In most cases, there are exceptions, but in most cases, when when the entire workflow is digital, we're square all the way through. There are things like HDV, that the HDV standard records to a 4:3 storage size, but is intended to be displayed 16:9. So there are things like that. But.
And really, I guess to draw the point home with that, the only way to definitively know would be to do additional testing by doing things like going back out to the scene, introducing a spherical object to the recording device, and ensuring that that spherical object appears spherical on your results. What we're looking at here is a much quicker way of looking at the way that the standards work and what's more commonly done to speed up the workflow and get the results that we need. But in cases where it might be really important, it might be relevant to go back out to the scene and do test recordings like that. I see another question about whether or not this webinar is going to be available afterwards online, and the answer is yes. We've been uploading each of these webinars to our YouTube page. So let me quickly here, let me pull up the website address for those of you who don't have that. We will be sending out an email afterwards as well that will give you this, but let me go here to put this YouTube. It should be one of the first links here on the video side for this webinar. So here we go. If you search under YouTube for video interrogation, it should be one of the most recent links. And this is a webinar that we held last month, very similar format to the one that we held this month, and we will continue to do these moving forward. We also did hear word through one of the attendees that LEVA is going to be offering 1 hour of credit for recertification for attending these webinars. So please do keep notes that you've attended these. We'll be talking about some additional ways that we're going to validate attendees moving forward. But for now, please just record that you attended the webinar on this date and that it was held by both myself, Andrew Fredericks, and by Larry Compton. So that we'll make sure that we can give you the certification that you need for that to use it for your application. So we've gone about 10 minutes over what I was intending here, so I apologize. I'm going to have to cut the questions a little bit short. If you have any additional questions that you want to ask to myself directly, please feel free to email me. Use the info@inputace.com email address to reach out to Larry. Larry's with Ocean Systems, and you can reach out to him at larry@oceansystems.com. Either one of us should be able to help address any additional questions you have about this webinar. So thank you again for attending. We look forward to doing another webinar next month. We hope that you'll attend. We'll be announcing the subject here momentarily. Also, as we close this webinar down, you'll be presented with a survey. We would definitely appreciate if you attended that. So thank you again very much for attending. We hope this was informative, and we look forward to seeing you next time. Bye-bye.